Hi everyone, my name is Andrés Munoz, and I'm here to talk to you about the pitfalls of label differential privacy. This is joint work with my co-workers Róbert Busa-Fekete, Umar Syed, and Sergei Vassilvitskii at Google. Let me start by describing the current data and privacy landscape. As everyone knows here, data is fundamental, not only for researchers, but for companies, drug developers, scientists, and even politics and decision-making. The value of data is clearly very high. However, unregulated access to data creates a lot of risks for individuals, in particular privacy risks, where people get to learn information that they shouldn't. Fortunately, we have a powerful tool for protecting data called differential privacy. This is essentially the de facto tool for data analysis at this point. Any practitioner of differential privacy, however, knows that in spite of the promises of differential privacy, the utility of data truly diminishes a lot once we start using the correct values for differential privacy. As a response, researchers have continuously tried to introduce different relaxations of differential privacy, not always understanding what the full implications of this are. On this talk, I'm going to focus on what's so-called label differential privacy, try to understand the complete risks for users that label differential privacy can induce. So at a very high level, the label differential privacy is the following. If a user has what's so-called public information or public attributes, such as gender, zip code, or age, and a sensitive attribute, such as a disease or my income, and a researcher wants to train a model to predict a sensitive attribute without learning information about individual users, right? Ideally, what we would do is share this data set of public and sensitive attributes with all of the information noised so that the researcher wouldn't be able to figure out information about users. Okay, in practice, however, this wouldn't work. The utility of the predictive model would generally be very bad unless it's a very, very simple case. And so what researchers have proposed is to use noise only on the sensitive attribute. So if it's a disease, basically treat this as randomized response. Otherwise, the information on the public, so let's say the public information remains unnoised. So the question now is, how private can this be made? All right. Let's start by a thought experiment. I think some of you must be familiar with the randomized response setup. This is basically the first appearance of differential privacy in the literature. And it goes as follows. Suppose that we want to do a study, for instance, on the incidence of lung cancer. So we have a large population, and we ask them the following question. Do you have lung cancer? Of course, this is a sensitive attribute of the user, so the user will not likely reveal this information about themselves. So to protect their privacy, we do the following thing. The respondent gets to flip a coin. The probability of heads is going to be equal to P. If the coin falls heads, then the person has to answer truthfully. If it falls tails, then they get to say yes or no uniformly at random. Notice that because there's some randomness in there, when a person sees the record, it's impossible for them to derive whether or not this person actually has cancer. More importantly, for moderate values of P, the respondent information is fully protected by a randomized response, and the data collector can get accurate aggregate information about incidence of lung cancer. So there's a nice way to debias this data and actually collect the information the data collector care about without exposing identity or information about these users. So this is great. This is how differential privacy should be done. How is it actually done in practice is, well, we do the same experiment as before, except that now respondents get to provide their gender, their age, and their smoking status. Randomized response is only applied on the lung cancer information, but the report that we send out is both on noise and unnoised information. My question to you is, do you believe privacy protection guarantees are the same? Let's try to break it. Let's try to do what's called inverting the randomized response. Suppose that the data collector already knows the posterior distribution of lung cancer given smoking. Suppose that we know that function, f of smoking. Well, if I know that information, it's very easy to estimate p of a user having lung cancer given the report. I can simply just use f of smoking and invert this. So here is the theorem of how an attacker could learn something about you. If f of smoking is close to 0 or 1, I'm going to ignore whatever you reported, and I'm just going to infer that you have lung cancer based on f. All right? If f of smoking is not close to 0 or 1, then randomized response actually provides privacy protections. Now you're going to argue with me and say, well, the data collector already knew f of smoking, so this isn't really a privacy violation. This is just correlations being applied. And you would be right if the attacker already knows f of smoking. The question that we want to focus on here is, if they don't know it, could they learn it? Turns out that yes, they can. With enough data, it is possible to estimate f of smoking accurately by debiasing the reports in the same way that we would have done it before having the public attributes. Now, here's a nice learning trade-off is that if f of smoking is close to 0 or 1, then the experiment will leak information about the user. This is risky and is probably bad for users. On the other hand, if it is not to 0 or 1, well, the experiment does not leak particular information about a user, so that is good. But at the same time, this is also likely going to be a bad predictor. So why would we even care about learning this information? So this tension is what we're trying to study and trying to generalize to more, to general cases. So in the general case, we have access to public feature vectors X. Again, think of gender information, like gender, zip code, age, and a true sensitive label, Y. So again, lung cancer, for instance. And what the report is going to contain is both the public features X and a randomized response of the sensitive label Y prime. This randomized response can be done with some probability P to ensure a certain amount of privacy. The question is, what can we say about the privacy protection of users if I get several samples from this generative process? The questions we want to answer is, how do we quantify the trade-off that I presented before in general? Do all users get the same protection, or do users that are easier to classify have more risk of leakage? Can we estimate the true privacy risk of label randomized responses? So here are the answers to these questions. How do we quantify this trade-off in general? We need to use a regression function. This is simply the posterior distribution of y prime is equal to 1, condition on x equal to x. The true privacy leakage increases by log of eta of x divided by 1 minus eta of x. So as eta goes to 1 or to 0, we see that this log goes to infinity. That's how fast privacy gets degraded. Do all users get the same protection? No, it depends on the regression function. Again, as we expected before, if you're closer to 0 or 1, your protection is less. If you're closer to 1/2, your protection is more. Can we estimate the true privacy risk of label randomized response? Yes, you can do this using nearest neighbor estimators. But can attackers then estimate the regression function? Yes, they also can do it using nearest neighbor estimators and then obtain information about the user. So here is an example of 4 data sets where we applied noisy randomized response by using a noise level of p equals 0.01. Here we are plotting epsilon, as in epsilon differential privacy. So higher epsilon means less privacy, lower epsilon means lower privacy. Private values of epsilons are generally thought to be somewhere around 1, less than 1, or at most 2 or 3. On the y-axis, what you see is a fraction of users with a privacy leakage higher than epsilon. Notice that for a noise level of p equals 0.01, the expected privacy protection from randomized response, if no features were released, is of epsilon around 2, which is a reasonable value for privacy protection. However, for several of these data sets, a big chunk of the population has privacy protections that are weaker than epsilon equals to 5, which is starting to get to a place of high risk. So this plot shows you the true cost of label differential privacy on users and the particular risk that they may have. So just some thoughts that I want people to have at the end of this talk are the following. One is that you should think that label differential privacy is not uncommon. It's actually very, very common, because unless you're working on what's the so-called shuffled model, records usually have a user identifier. And this user identifier can then be used to gather a bunch of other features. Now, should we be thinking about how to measure true privacy risks of randomized response for these scenarios? Is there a way to maximize the amount of information we provide for learning while protecting user privacy? Or is this a zero-sum game? That is, if data is useful for learning, then it has to be easy to invert privacy. That question, we don't fully have the answer. I think what we provided is a smallest step in that direction. Just to conclude, differential privacy is a powerful tool for data analysis. However, we should be treating it with care, as several relaxations of differential privacy have been proposed to make it more practical. But we don't completely understand their implications. In this work, we demonstrated that one of them, label differential privacy, actually does have higher privacy leakage risks than expected. We believe that users must be made aware of these true risks of differential privacy models that are not as strict as the original definition. Thank you very much.
So just wondering, like, how the differential privacy is going to impact on like the social media data, like Twitter, where there is so many gender attributes, there are multiple variety of attributes which people put on there. What is your take on that? Like, what are your views on that?
So yeah, this is a very good question. I think differential privacy is it's a great tool for technically enforcing some of the requirements to share information. However, I think as I point out in the talk, it takes a little bit more than just this epsilon parameter to really quantify how much privacy loss is out there. So I think the way that this is going to affect platforms is that there's going to have to be a more in-depth discussion as to how we can inform to the users what exactly happens when you put all of this information out there, right? Like it can be very bad if you allow everyone to see everything about you and then you sort of complain about not having privacy, right? So I think this is an evolving field, and honestly, good regulation in privacy for this type of platforms is very young. So I think as time goes by, better and better regulation is going to show up. And I think that better regulation is going to be tied up to better technical results from this community, and then better ethical understandings of what privacy is. So I'm very excited about the next 10 years in privacy.
Great, thanks. So we have another question for Andrés. Could you comment on any possible connections between the idea of this randomized experiment and information theoretic notions, as in considering this experiment as setting up a noisy channel? Are there any IT concepts that show up in trying to prove the bounds on the amount of information leakage?
Yes, so I can definitely talk to that. The information theory, I think, is very connected to privacy. They're one and the other, or like they're hand in hand, and they just are speaking maybe different languages, and that's why there's this idea that they're not as connected. But differential privacy, at the end of the day, is understanding the distance between two distributions, sort of parameterized by some data set, right? And information theory gives us a bunch of techniques for bounding this distance, right? That's how we know the KL divergence, Remy divergence, all of these multiple information theoretic notions allow us to calculate things in differential privacy. At the same time, I think differential privacy allows us to bound the amount of information that is shared with, like you can definitely bound the amount of information as a function of the epsilon parameter. What I think is interesting here for the experiment is that in the case where you don't have any features, I think the information that you get can be very nicely quantified by differential privacy. When you include some features, this quantification of the information that you get is interesting. And I think the perfect case is that if I have a perfect predictor that says gender is going to be completely correlated with cancer, it's very easy to understand sort of, oh, wait, maybe I shouldn't be releasing gender out there because it's going to really correlate with cancer, right? This sort of gray area where it may not be perfect correlation, but it might be like somewhat correlated, does provide new information to you that you didn't have. And that's where we need to be concerned about, like, is this enough information that we're going to be sending out? Is this going to be damaging information? How do we quantify this? And I think this connection is going to start making, it's going to be becoming more and more clear as time goes by, again, between this information theory and privacy. I don't know if that answered the question. I hope it did.
I hope that, like, thanks.